Let's take a look at some more examples using our derivative rules. Let f be the function defined by f of x equals 4 minus e to the x. Find an equation of the line tangent to the graph of f at the point where x equals 0. When we want to write an equation of a line, we are going to need a point and a slope. Now they gave us part of the point. They gave us the x value of the point. We need to find the x and the y coordinate of the point. So we plug in the x value into the function. F of 0 is 4 minus e to the 0, which is 4 minus 1, or 3. So now we have the point 0, 3. We also need the slope for the equation of the line, and the slope, which we often call m, will be the derivative of the function at the x value 0. Let's start by finding f prime of x. 4 is a constant. The derivative of a constant is 0, minus e to the x is the easiest because it's itself 0 minus e to the x, or negative e to the x. Now we want the slope at the x value 0, so we're going to plug in 0 for x, negative e to the 0, which makes negative 1. Now that we have the point and the slope, we can write an equation of the tangent line. I prefer to use point-slope form. I think it's the easiest. Y minus the y coordinate equals the slope times x minus the x coordinate. Now this is an equation of the tangent line, so technically we're done. But just to practice being able to recognize what other forms you might see, of course x minus 0 is unnecessary, and of course multiplied by negative 1 is unnecessary. We can simply write this as y minus 3 equals negative x. And that's also an acceptable answer, an answer that you might write and an answer that you might see if it's multiple choice. Often, people also like to put their answers of equations of lines in standard form, where the x and the y are on the same side. So if we add x to both sides and add 3 to both sides, we end up with the standard form x plus y equals 3. Also an acceptable answer. Now notice the extra work I had to go through to get one of these new forms. You are always allowed to stop once you've plugged it into point-slope form if it's free response. Let's look at this example. Use the function f of x equals x cubed plus 2x squared minus 15x plus 14 to do the following. A. Find the points, if any, where f has any horizontal tangent lines. Remember that a horizontal line has a slope equal to 0, which of course means the derivative will equal 0. So that's where we'll begin, finding the derivative of our function. F prime of x equals, using our power rule for x cubed, we multiply the 3 in front, subtract 1 from the exponent to get 3x squared. Plus, the exponent is 2, multiply that to the front, makes 4, and subtract 1 from the exponent is 1, that I don't need to write. Minus 15 is a constant multiple, x to the first becomes x to the 0, which is 1. And finally, 14 is a constant, and the derivative of a constant is 0, so I'm not going to write that part. I want my derivative to equal 0, since a horizontal line has a slope of 0. So I set my derivative equal to 0. This is a quadratic that can be factored. The factors are 3x minus 5 and x plus 3. Setting each factor equal to 0, we get that x equals 5/3 and x equals negative 3. Now we have the x coordinates where there is a horizontal tangent line, but they want the points where there are horizontal tangent lines, which means we need the y coordinate that goes with these x coordinates. So we're going to need to plug in each of these x coordinates. So I'm going to find f of 5/3, which means I plug 5/3 into that original function. 5/3 cubed plus 2 times 5/3 squared minus 15 times 5/3 plus 14, and that comes out to negative 22/27. So that means one of my points is 5/3 negative 22/27. I also have negative 3 to plug in. So just like we did for 5/3, we plug negative 3 into the function, and we come out with 50. So the other point is negative 3, 50. And these are the points where the function f has horizontal tangent lines. B, find an equation for each horizontal tangent line. Now remember that we already know the slope is 0, and anytime it's a horizontal line, it's simply y equals a number. So looking at the y-coordinates that we got for each of the points, we simply are going to have y equals negative 22/27 and y equals 50. Two horizontal tangent line equations. Part C, solve the inequalities f prime of x is greater than 0 and f prime of x is less than 0. Describe what this means about the function f. We already have taken the derivative, which is 3x squared plus 4x minus 15. Where is it greater than 0? Well, again, we start with its factors, like when we were trying to solve where the derivative equals 0. When we are trying to figure out where this derivative is greater or less than 0, we first want to start with where does our derivative equal 0? And that happens when x equals 5/3 and negative 3. Let's set up a chart that helps us figure out when our derivative is greater than 0 and when our derivative is less than 0. We know that our derivative equals 0 at negative 3 and 5/3. Up top, we're going to write the intervals that are shown on each of the sides of the zeros. So for example, before negative 3 is the interval negative infinity to negative 3. Between those two zeros is the interval negative 3 to 5/3. And after 5/3 is the interval 5/3 to infinity. Now, for each of these intervals, we are going to determine the sign of the derivative, f prime. On this first interval, between negative infinity and negative 3, the sign of f prime will be the same no matter where we are. So if we pick a little test value in that interval, such as negative 10, and I check out the sign of the factors. So in my head, I can do this. Negative 10 times 3 is negative 30, and I'm subtracting a negative number. That makes a negative. And negative 10 plus 3 still makes a negative number, and a negative times a negative makes a positive. So the sign is positive on this first interval. On the next interval, what's a number between negative 3 and 5/3 that I can think of? 0. And if I plug in 0, I get a negative for the first factor and a positive for the second factor. So I'm getting a negative times a positive. That makes a negative. On the third interval, something between 5/3 and infinity, like positive 10, plugged in here would make a positive, and plugged in here would make a positive. And that is a positive times a positive, which makes a positive number. So we can now give our answer that f prime is greater than 0 on two intervals. This one where we said positive and this one where we said positive. Negative infinity to negative 3, union with 5/3 to infinity. F prime is less than 0 on that interval where we said f prime is negative. Negative 3 to 5/3. So we answered the question, where is f prime greater than 0 and where is f prime less than 0? Now we can help use this to describe what this means about the function f. So remember, when a derivative is positive, that means that the slope of the function is positive, and therefore the function is increasing on those intervals. When the derivative is less than 0, that tells us that the function is decreasing, specifically on those intervals. Let's take a look at this example. Let f be a function defined by f of x equals 2x minus x squared for x less than or equal to 1, and x squared plus kx plus p for x greater than 1. For what values of k and p will f be continuous and differentiable at x equals 1? Now, of course, we don't really have to be asked continuous, because if we're asked if the function is differentiable, that means our function must also be continuous. Let's start with when our function will be continuous. So remember that our definition of continuity said the function value has to exist, the limit exists, and those two equal each other. If the limit exists for a piecewise function, we want to make sure that the left-hand limit equals the right-hand limit as x approaches 1. Then we'll know that the limit exists. So that's what we're going to make sure that we do. The limit as x approaches 1 from the left for f of x will equal the limit as x approaches 1 from the right of f of x. Less than 1 is the left side of 1, and greater than 1 is the right side of 1. So we'll be using 2x minus x squared for the limit from the left. So 2, instead of x, we're going to use substitution and plug in the 1. 2 times 1 minus 1 squared. The right-hand limit uses this expression. So we plug in 1 for the x's. 1 squared plus k times 1 plus p. Let's simplify this side. 2 minus 1 makes 1 equals 1 plus k plus p. Subtracting 1 from both sides leaves us with 0 equals k plus p. Now notice we've neither solved for k nor p, so we need something else to help us figure out k and p. Let's take a look at the other part of the story. The function must be differentiable. To be differentiable, that means the derivative from the left must equal the derivative from the right. So let's show the notation to do that. d dx, the derivative with respect to x of the function from the left side of 1, 2x minus x squared. Now specifically, we want the derivative when the x value equals 1. We want that to equal the derivative with respect to x from the right, x squared plus kx plus p when x equals 1. Now let's do each of these derivatives. Using our power rule, we get 2 minus 2x, and we want that evaluated when x equals 1. And our derivative for this, using our power rule, 2x plus k being a constant times x is just the constant. P being a constant, the derivative of the constant all by itself is 0. And we want that at x equals 1 as well. Now we plug in the 1 where the x is. 2 minus 2 times 1 equals Plug in the 1 over here, 2 times 1 plus k, and let's do some simplifying. 2 minus 2 is 0, equals 2 plus k, so k must equal -2. We've got one of our answers. We're going to use that to help us find the other answer. Plugging it back into that other equation, 0 equals -2 plus p, we see that p must equal 2. And there we have it. Thanks for watching.